Okay, so question 1. The functions f and g are defined as f is 2 sine x plus 3 cos x, and g of x is e to the 3x minus 1. We want to find f of g of 0, right? So this notation here, fg of 0, is what we call a composite function. So we've got the function g inside of the function f. That's really what it means. So what we could do is we could find g of 0, that thing, and then we're going to substitute that into f. So what's g of 0? G of 0 is equal to e to the 3 times by 0, so that's e to the 0 minus 1. And e to the 0 is 1, because anything to the power of 0 is 1, and 1 minus 1 is 0. Okay, so then what we're going to do is we're going to substitute that into f. So f of 0 is then equal to 2 sine 0 plus 3 cos 0. And sine 0 is 0 and cos 0 is 1. So we've got 0 plus 3. Okay, so we can write that fg of 0 is equal to 3. Okay, then the next part B, is we want to find g of x. So again, this is a composite function. What we're doing is we're putting the function g inside of the function g, like that. What that means is that in the function here, every time we've got an x, we're going to replace it. So every time we've got an x, we're going to replace it with e to the 3x minus 1. In other words, the whole function. And if we do that, we're going to get e to the power of 3, bracket, e to the 3x minus 1, minus 1, right? So you can see, hopefully here, that guy there is the function g. And what we've done is we put it inside of the function g, like that. Okay, and that's going to be our answer for part B. Okay, so this is part C. We want to solve the equation g inverse of x is equal to a third ln 5. So what we're going to do, I think probably the best thing is just find the inverse function of this. How do we find an inverse function? Well, what an inverse function does is it finds the inputs in terms of the outputs, right? So let me just quickly try to explain that. Imagine we've got a function here. That function is f. We put in an input x and we get an output y. Well, the whole job of the inverse function is to take our outputs and give us back our original inputs, right? So that's what it does. It kind of reverses the x and the y's. So for example, if x was 2 and the original function gives us an output of 7, that means that if we would put 7 into the inverse function, we should get an output of 2. So when it comes to computing the inverse function, in other words, or trying to find it, really what we're doing is we're trying to rearrange this thing so that we make x the subject, right? So in other words, we go from y back to our original x. So that's what I'm going to do. I'm going to write y is equal to e to the 3x minus 1, and I'm going to rearrange it to make x the subject. So I'm going to add 1. Like that, e to the 3x. I'm then going to use, convert this to logarithmic form. So 3x is equal to ln y plus 1. Then I'm going to divide both sides through by 3. So x is equal to a third of ln y plus 1. And then the final step for the inverse function is, in the end, we just replace the y with x, because in a way, like the output y becomes our new input x. Sorry. So that is a third ln x plus 1. Okay, then what we want to do is we want to set this equal to a third ln 5. So a third ln x plus 1 is equal to a third ln 5, which if that's the case, then ln x plus 1 is just the same thing as ln 5. And that means that x plus 1 is equal to 5, which means that x is equal to 4. And that will be our answer. Okay, so here we are in question 2. We want to find the values of k for which this curve is completely above the x-axis. Now, I think it's probably helpful first if we get an idea of what this actually means and what it looks like. So I'm going to draw out a quadratic, and I'm going to draw out a quadratic which is completely above the x-axis, right? So let's say we got that quadratic there. Now, if that quadratic is completely above the x-axis, it means that there are no roots, right? There are no roots because there are no x-intercepts. Can you see? Never crosses the x-axis, so there are no roots, no x-intercepts. So this means that the discriminant of that quadratic must be negative, right? So we need to recap this idea of the discriminant. The discriminant is given by b squared minus 4ac. And hopefully what you will remember is that there are basically three different outcomes for the discriminant that determine the number of roots that the quadratic will have. So the discriminant can be positive, it can be negative, and it can be 0. And that's going to determine the number of roots. So if the discriminant is positive, we've got 2 distinct roots. If the discriminant is negative, we've got no roots. And if the discriminant is 0, we've got 1 repeated root. Now, perhaps you might be wondering why that is the case. You never really understood it. Well, let me just try to explain. It really goes back to the quadratic formula. The quadratic formula is minus b plus or minus the root of b squared minus 4ac all over 2a. Now, where do you see the discriminant in that formula? We see it inside of the square root. So now let's imagine 3 different cases. Let's say that b squared minus 4ac is negative. Well, if it's negative, the thing inside a square root is negative, and we cannot square root a negative, which means that this is going to have no solution. So we will have no roots. Well, now let's imagine that the discriminant is 0. So this thing here is 0. Well, then our solution will be minus b plus 0 divided by 2a and minus b minus 0 all upon 2a. Well, those things are exactly the same, aren't they? It's the same thing. It's minus b upon 2a. So we've got 2 solutions which are identical, or another way of saying that is we've got 1 solution which is repeated. Okay, and then the last case, let's say that our b squared minus 4ac is positive. Let's say it's 9. Well, then if we square root that, we're going to get 3 here. So we're going to get minus b plus 3 and minus b minus 3 upon 2a. And those are 2 distinct solutions, right? They're 2 different things. So hopefully this should make a little bit more sense for those of you who haven't understood it the first time round. Now, how can we therefore solve this problem? Well, the first thing is we want to identify what a, b, and c are. So a is 1, because it's the coefficient of x squared. B is k, it's the coefficient of x. And c is 4k minus 15. And now we've got to do is just got to put that into the formula for the discriminant and say that we want the discriminant to be negative, so we want it to be less than 0. So let's plug everything in. B squared is k squared minus 4 times by a, which is 1, times by c, which is 4k minus 15. And let's expand that all. We're going to get k squared minus 16k plus 60 is less than 0. And sometimes I think a lot of people basically then guess the inequalities at the end. So what we're going to do is we're going to avoid that by sketching out this quadratic and showing ourselves where the quadratic is less than 0. But before I do that, I'm going to factorize this guy. And if I factorize him, I should get negative 6 and negative 10. And the reason for that, right, is negative 6 times by negative 10 is positive 60. And negative 6 plus negative 10 is negative 16. So that works out fine. Now, what does this quadratic actually look like? Well, the quadratic is going to look something like this. Right, so let's say here is whatever 6, and here's 10. It's not really to scale, doesn't really matter. So the quadratic is going to look something like that. Oh dear, sorry about that. It's kind of hard to sketch on the tablet. There we go, like that. That's our quadratic, right? So that's this thing here. Well, where is that quadratic less than 0? In other words, where are the y values less than 0? Well, it's everywhere here, isn't it, right? Here, the quadratic is less than 0. So what we want to do is we want to find the values of k that give us that part of the graph. Well, that's going to be given by these values here, isn't it, right? Everything between 6 and 10. So we can say the values of k that are our solution is k must be greater than 6 and less than 10, right? Very often what I find is students write something like k is less than 6 and k is less than 10, right? Because they just treat this like it's an equality and then they're not sure how to deal with the signs. If you're really unsure, can I strongly suggest that what you do is you sketch out your graph. Right? If you sketch out the graph, then you can understand why we are looking at this region here between 6 and 10. All right. Okay, question 3, which is a logarithmic question. May I suggest that the way to deal with this is to use a substitution. So we've got log base 2x and log base 2x here, and log base 2y and log base 2y there. So I'm going to say let big X equal log base 2 little x, and big Y equal log base 2 little y. And the reason for doing that is then these pair of equations become 3 big X plus 2 big Y is equal to 24, and 5 big X minus 3 big Y is equal to 2. And it's just a lot easier to solve those equations, which are linear equations. Okay, so how am I going to do that? Well, I think I generally encourage using elimination. So we're going to eliminate either x or y. I think what I'll do is I'll eliminate the y's. So I'm going to do that by multiplying the top equation by 3 and the bottom equation by 2, so that we get 6y in both. So if I multiply the top equation by 3, I get 9x plus 6y. Okay, 24 times by 3. Well, 20 times by 3 is 60. 4 times by 3 is 12. So that's going to be 72. And then the second equation I'm going to multiply by 3, so I get 15x minus, sorry, I'm multiplying it by 2, aren't I? Stupid me. That was very silly. So it's going to be 10x, beg your pardon, minus 6y is equal to 4. Let me just double check that. Times by 2, 10x, times by 2, negative 6y, times by 2, positive 4. Okay, so how are we going to deal with this? Well, we can add up both of these equations. Why are we going to add them up? Because 6y plus minus 6y is 0, so we're going to eliminate those y's. And what we're going to end up with here is therefore 19x is equal to 76. And if we divide both sides by 19, then I think what we should get is 4, right? So 19 times by 4 is going to be 76. If you think about that, 20 times by 4 is 80, then minus 4 is 76. So hopefully you could also do that in your head. Okay, if x is 4, we can substitute in. I'll substitute it into the top one, I think. So 3 times by 4 is 12. So 12 plus 2y is equal to 24. So 2y is going to be equal to 12, y is going to be equal to 6. Okay, so we've got big X and big Y. Well, how do we go from there? Well, we remind ourselves, don't we, that big X was log base 2 little x. So log base 2 little x is equal to 4. And big Y was log base 2 little y, so that's equal to 6. So what's x going to be equal to? If we convert this to exponential form, it's going to be equal to 2 to the 4. And y, if we convert it to exponential form, will be 2 to the 6. And 2 to the power 4 is going to be 16. And 2 to the power 6, well, we just times it by 2 and times by 2 again, so that will be 64. So my x should be 16, my y should be 64. I'm just going to check the mark scheme, make sure that I have got that all right. Let's see. 16 and 64. Correct. Okay, so here we are in part B with an exponential style of question. There are a couple of things here that I think you'll need to know. So the first thing is you need to know the indices rules. So let's just recap the relevant one. If I've got a to the power of x and I divide it by a to the power of y, then I subtract the powers, I get a to the power of x minus y, like that. It's quite common for people to confuse that and think it's a to the power of x divided by y. That's not true. So make sure you understand and are comfortable with those indices rules. The other thing is recognizing that numbers like 512 are going to be powers of 2. Okay, so hopefully you'll know something like 2 to the power of 3 is 8. Right, and if we just go down, say 2 to the power of 4 is 16, and 2 to the power of 5 is 32, 2 to the power of 6 is 64, 2 to the power of 7 is going to be 128, and then 2 to the power of 8 is 256, and 2 to the power of 9 is going to be 512. So I'd say most people kind of know the powers of 2, probably up to 64, maybe 128. But I think some of you may not be comfortable up to 512. But if you notice that on the left-hand side, you've got powers of 2 here, it's probably a reasonable bet that this guy is going to be a power of 2. And remember, part A was log base 2 as well. So what you probably want to do is want to go on your calculator and just see if you can get that as a power of 2, because then everything's going to simplify. All right, then, how can we do this? Well, first thing is we use the this rule over here. So I'm going to subtract the powers. So I get 2 to the power of t plus 4 minus 1 minus 2t. Right, so I subtract the whole thing, and remember, put it in brackets, right? Because you want to remember you got minus 2t. That's a common error, and that's going to be equal to 2 to the power of 2 to the power of 9, wasn't it? 2 to the power of 9. Well, if that's the case, right, then these two powers must just be the same thing. Okay, so now we can just write t plus 4 minus 1 minus 2t. Well, that guy must be equal to 9. So if I simplify that, I've got t minus 2t. That's 3t. I've got 4 minus 1, which is plus 3. So therefore, 3t is going to be equal to 6, and t will be equal to 2. Okay, so t is equal to 2 should be our answer. Okay, so here we are in question 4, which is an integral question. Now, in this type of question where you've got a single term on the denominator, the best thing to do is to expand the numerator and then cancel off terms. Okay, so let me just demonstrate that. We've got the integral here of between 3 and 5. I'm going to expand x minus 1 squared. So that's going to give me x squared minus 2x plus 1. And that's going to be all divided through by x cubed dx. And that means that I can split up that fraction into 3 separate fractions, right? I've got x squared divided by x cubed. I've got minus 2x divided by x cubed. And I've got plus 1 divided by x cubed dx. Now, if I cancel off, right, I've got x squared divided by x cubed. Well, I could subtract the powers, right? Do 2 minus 3 gives me negative 1. Or I could just divide top and bottom by x squared. Either way, what I'm going to end up with is 1 upon x. Next, if I divide top and bottom of this by x, then I'm going to get 2 upon x squared, and 2 upon x squared can be written as 2x to the power of negative 2. Now, there's a reason why I've written these two guys differently, and I'm going to explain that in a second. And 1 upon x cubed can be rewritten as x to the power of negative 3 dx. Now, as I was saying, I have chosen very deliberately to write these two in indices form, right? So I've written them as x to the power of negative something, and this guy here, not as x to the power of negative 1, but as 1 upon x. Now, why is that? Because this guy is going to integrate differently to the others. Okay, so this guy over here integrates to give ln, whereas these guys, they integrate the normal way by adding, or I say the normal way, right, as if there's a normal way, but by adding 1 to the power and by dividing by the new power. So we need to understand before we do this that we've actually got two different methods of integration here that are going to look very similar, and hence there's a trap that we need to be aware of. So let's do that. If I integrate 1 upon x, I'm going to get the natural log of x. And if I integrate 2x to the power of negative 2, well, I add 1 to the power, so I get 2x to the power of negative 1, and I divide through by negative 1. And with x to the power of negative 3, I add 1 to the power, so I get x to the power of negative 2, and I divide by negative 2. And this is a definite integral, so I need to remember to put in the square brackets, and the boundary is 5 and 3. Now, I'm just going to tidy this up before I do anything. So I'm going to write this now as ln x. Minus divided by minus is a plus. So, and then x to the power of negative 1 is same as 1 upon x. So I'm going to write that there as 2 upon x. And I've got a positive divided by a negative. So I got minus 1 upon 2, right? Because this guy's like a half, right? Divide by 2. And x to the power of negative 2 is the same as 1 upon x squared. Now, why have I converted back from indices form, right? So I converted to indices form when I wanted to integrate because it helps me to understand what I'm doing to the powers, and I would strongly recommend that you all do that. But now I've got out of indices form, I've written these as fractions because I'm going to be substituting in the upper and lower bounds, and it will be much easier for me to understand if I've written them as fractions. So what I want you to see, and one of the skills that hopefully you should develop, is sometimes indices form helps and sometimes fractions help. And so you should be comfortable with moving back and forth between the two, depending upon what you're doing. So if you're integrating, indices form, best thing. If you're substituting in values, write it as fractions. That will make your life easier. Okay? All right, so let's substitute in our upper bound. So if I substitute in 5, I'm going to get ln 5 plus 2 upon 5 minus 1 upon 2 times by 1 upon 5 squared, which is 25. And then I'm going to substitute in my lower bound. So I'm going to subtract off ln 3 plus 2 upon 3 minus a half times by 1 upon 3 squared, which is 1 upon 9. So, okay, let's try to combine all this. I've got ln 5 plus 2/5 minus 1 upon 50 minus ln 3, so I'm now opening up the bracket, minus 2/3 minus, not minus, plus, right, because we've got minus, plus 1 upon 18. And then I'm going to try to combine the fractions as best as I can. So I'll write ln 5 minus ln 3, put those two guys together. I'm going to sort those out in a moment. I'm going to change this so it's got the same denominator as the 50. So I've got 20 upon 50 minus 1 upon 50. And then I'm going to change these guys so it's got the same denominator as well. So I'm going to times up by 6, I think, there. So that'll be minus 12 upon 18 plus 1 upon 18. And here what I can do is I can use my log rules, right? If I've got log A minus log B, I can rewrite that as log A over B. So I've got ln 5 upon 3 plus 19 upon 50. And then I've got negative 12 upon 18 plus 1 upon 18, so that's minus 11 upon 18. Well, I think that's probably about as far as I'm willing to go without the aid of a calculator. So let's see if we can simplify that now. Okay, and if I put that into the calculator, what I got was negative 52 upon 225. So we get ln 5 upon 3 minus, what was it again? Let me just see, negative 52 upon 225. And that should be our answer. Now, I just on that, I know it seems like a bit pointless me trying to simplify fractions and so on, and in the end I had to use a calculator. But one of the mistakes I often see students make is you're trying to type everything into the calculator from that line. Now that's actually quite a long thing to type in, and you end up making mistakes because it's so easy to hit 3 instead of 2, so easy to write minus when you meant plus. So can I suggest that you do sort of get into the habit of trying to work out everything you can, because actually your brain is often a lot better than a calculator. And then when you get to the final step, then you can use a calculator here, and hopefully you can be more confident that you're right. Okay, so in general, even though it seems a bit silly for me to be doing things manually, actually, I think it's better for you to be in the habit of doing that because I think you actually make fewer mistakes when that happens. Okay? Okay, here we are in question 5. The curved surface area of a cylinder with radius r and height h is 2 pi r h. A closed cylinder has radius of r and volume of 1,000 centimeters cubed. Show the total surface area of the cylinder is given by this. Okay, now I think it's often helpful just to actually draw out a cylinder so you've got a rough idea of what's going on here. How are we going to find the volume of the cylinder as a formula? Well, what we would need to know is we need to know the area of the circle on the bottom. So the area of a circle is given by pi r squared, and then we've got to times it up by the height h. So we've got a formula for the volume of a cylinder, which is pi r squared times by h. Now, we're told that the volume of this cylinder is 1,000. So we can write that 1,000 is therefore equal to pi r squared h. And we can rearrange that to get h is equal to 1,000 over pi r squared. Okay, that will be a little bit useful in a moment. Okay, then. Now, the surface area. How do we find the surface area of our cylinder? Well, firstly note that this is a closed cylinder, so we need the area of both the bottom and the top, right? If it was an open cylinder, then we just do the bottom because we assume that the top here is like open like a glass. So we've got the area of a circle, which is pi r squared, but we've got two of them on top and bottom, so it's 2 pi r squared. And we're told here that the curved surface area is given by 2 pi r h. Now, if you're wondering why that's the case, right? The curved bit is this bit here, by the way. You take the length on the bottom, which is the perimeter of a circle, that's 2 pi r, and then you times it up by the height h. Okay, so here we get 2 pi r h. Okay. Now then, we want a formula that's just got r's that's got no h's in it. So what we've got to do is we've got to get our expression here for h and substitute it in. And that's exactly what we're going to do. So we're going to get here 2 pi r squared plus 2 pi r times by 1,000 upon pi r squared. Okay, let me just do that. And if we do that, hopefully what you can see is that things cancel off, right? Pi cancels, r cancels, r cancels. And what we're left with there is 2 pi r squared plus 2,000 divided through by r. So we've shown what was required for part A. Right then, part B, we want to find the value of r, which makes this area into a minimum. And we should show that our value of r gives a minimum for this area. In other words, we want to show not just that we've got a stationary point, but that the stationary point in particular is a minimum and not a maximum. Okay, well, how are we going to do that? Well, we've got to differentiate this expression here for the surface area. Okay, so that expression was, let's write it out again. A is equal to 2 pi r squared plus 2,000 upon r, which I'll rewrite as r to the power negative 1. Okay, well, if we do dA dr, then what we're doing is we're finding the rate of change of a with respect to the radius. So if I differentiate this, I'm going to get 4 pi r, and then I'll get minus 2,000 r to the power negative 2, right? Because I bring the negative 1 down to the front and reduce the power by 1. Well, where do we get a maximum or a minimum? We get maximums or minimums when the derivative is equal to 0. So we can write something like stationary point when dA dr is equal to 0. Okay, and if I was to solve that, I get 0 is equal to 4 pi r minus 2,000 upon r squared, right? Again, I've converted from indices form, r to the power negative 2, to fractions because it makes it easier for me to deal with. Well, I think what I'll do is I'll get rid of that denominator. I'm going to multiply everything through by r squared. So this will become 4 pi r cubed minus 2,000. And so if I was to rearrange this, I'm going to get 4 pi r cubed. 4 pi r cubed is equal to 2,000. And therefore, r cubed is going to be equal to 2,000 divided by 4 pi. Well, if I divide 2,000 by 4, I'm going to get 500, right? So it's the same thing as 500 upon pi. And therefore, r is going to be equal to the cube root of 500 upon pi. Now, we would have to calculate the decimal value of that in a second. But let me just check the question. Want to find the value of r which makes this area a minimum. And we should show that our value of r gives a minimum for this area. Now, it actually doesn't ask us to find the value of the area at this in this question, so we don't need to substitute in our value of r into here and to get the area. But you need to be aware of that. They do often ask that in a question, and it's so easy to forget it when you're in an exam. So just remember that. Well, we want to show that our value of r gives a minimum. So what that means is we've got to differentiate this again and get the second derivative. So let me write out. dA dr is 4 pi r minus 2000 r to the power negative 2. So dA dr was equal to 4, silly pen, 4 pi r minus 2000 upon r squared, or 2000 r to the power negative 2. Just double check that. Yep. And if we differentiate this again to get the second derivative, d2a dr squared, then what we're going to get here is 4 pi plus 4000 r to the power of negative 3, which is the same thing as 4000 upon r cubed. Now, the key thing to remember about the second derivative is the second derivative tells us whether we've got a maximum or a minimum. And the condition is this, basically, if the second derivative, a double prime, is positive, then we have a minimum point. But if it is negative, then we have a maximum point. So what we've got to do is we've got to substitute our value of r, the cube root of 500 upon pi, into this expression here for the second derivative and see if we get a positive or a negative. Well, our value for r cubed is going to be 500 upon pi. That's a positive number, right? And so therefore this is going to be a positive number. And if we add 4 pi, we've got another positive number. So you might want to calculate it in full, right? So when r is equal to the cube root of 500 upon pi, then the 2a dr squared is going to be equal to 4 pi plus 4000 over 500 divided by pi. And I think that's going to be 4 pi plus 8 pi. In a way, it actually doesn't matter. The important thing is what we've got here is we've got a positive number. And if we've got a positive number, therefore we can say we have a minimum at that point. Okay, so let me just substitute the value for r into the calculator, so we should get the decimal value. Let me just find out what that is. 5.42. Okay, so 5.42. Just go up minimum when r is equal to 5.42 centimeters. Okay, and that should be your answer. All right, here we are in question 6. We have a particle travels in a straight line. Its displacement, s meters from the origin at time t seconds, where t is greater than 2, is given by this here, ln 4t squared minus 5 minus t. We want to find expressions for the velocity and the acceleration of the particle. Well, I think it's just helpful just to recap what's going on here. In these questions, we have 3 things. We've got displacement, which is denoted s. We've got velocity, which is denoted v. And we've got acceleration, which is denoted a. And we need to understand that velocity is the rate of change of displacement with respect to time, that is ds dt. Now, hopefully that should make sense, because what is velocity really about? It's about how quickly is our displacement changing over time. Same is sort of true with acceleration. Acceleration is the rate of change of velocity with respect to time. Therefore, it is dv dt. And again, that should kind of make sense, because what is acceleration telling us? It's telling us how quickly our velocity is changing over time. Now, what does this mean? This means if we've got displacement, velocity, acceleration in that order, then if we want to go down from displacement to velocity, or from velocity to acceleration, then we would need to differentiate. Okay, that's sort of fact 1. But then if we want to go up, if we want to reverse differentiation, then we would need to integrate, right? Because integration is the reverse of differentiation. So if you can understand this diagram here, this kind of core concept, then basically you should be able to understand the basics of these kinematics questions. Now, let's say we're starting with S, which is ln 4t squared minus 5 minus t. And we want to find velocity. Well, what is velocity? Velocity is ds dt, as we've just said. And so if that's the case, we need to differentiate this function. Well, how do we differentiate a natural log? We take the thing inside the log, which is 4t squared minus 5 in this case. We put it on the denominator, 4t squared minus 5. And then we differentiate that expression. So if we differentiate 4t squared minus 5, we get 8t. And we put that on the numerator, right? So we do like that. Then if we differentiate t, we get 1. So we got this expression minus 1. Okay, then, well, if we want to find a, then we need to differentiate velocity, which means we need to differentiate this expression here. Well, in order to differentiate that, we need to use the quotient rule. And what is the quotient rule? The quotient rule is used when we've got one function divided by another function. Okay, so what I'm going to do is I'm going to call the first function on the top, I'm going to call it u. So u is 8t. And the function on the bottom, v, is 4t squared minus 5. Okay? Now, we're going to need to differentiate both of these. So we get u prime is equal to 8, and v prime is equal to 8t. Okay? And what is the quotient rule? The quotient rule is v du, or vu prime, minus u dv all over v squared. Now, it's important to get that order right, okay? It's v du minus u dv. The classic mistake is to get the reverse order, u dv minus v du, and therefore get it wrong. So now what we need to do is we just need to substitute in. So I'm going to state that acceleration is dv dt. And therefore, we've got v times by u prime. So that's going to be 8 bracket 4t squared minus 5 minus u dv, which is going to be 8t times by 8t, all over v squared, which is 4t squared minus 5 all squared. Now, the mark scheme actually just accepts that as an answer, but I think in general it's a good idea for us to practice simplifying things. So let me just do that. We're going to expand out the bracket. So we're going to get 32t squared minus 40 minus 64 t squared. Okay. All divided through again by 4t squared minus 5 all squared. And if we were to simplify that, we get minus 32, beg your pardon, minus 32t squared minus 40 all over 4t squared minus 5 all squared. Okay, and then we can factorize out by negative 8 on the top, so we get negative 8 bracket 4t squared, t squared, let's make it nice, minus 5, sorry, plus 5 there because we factorized out negative 8, do beg your pardon, all over 4t squared minus 5 all squared. All right, so that would be a simplified version of A, but as I said, mark scheme is quite content to accept that in this case. All right. Okay, so we're in the next part of this question, which I think I'll do parts B and C together. Want to find the time when the particle is at rest. Well, what is rest? Rest is when the velocity is equal to 0. So we want to take our formula for the velocity, which was up here somewhere. So 8t upon 4t squared minus 5 minus 1. So 8t upon 4t squared minus 5 minus 1. I'm going to set that equal to 0. Well, I think I'll just double check I got my formula right. Yeah. And then what I'm going to do is I'll bring the 1 to the other side. So I get 1 is equal to 8t upon 4t squared minus 5. I'm going to multiply both sides by 4t squared minus 5. So I get 4t squared minus 5 is equal to 8t. And I will just move the 8t across. So 4t squared minus 8t minus 5 is equal to 0. And hopefully you should recognize that's a quadratic. Now, most of you all will probably use a calculator to solve the quadratic, but we're looking for two numbers that multiply to give -5. So it's going to be -5 and +1, or the other way around. And I think that's probably going to work this way. If I've got -5 here and +1 there, the reason for that is -5 times by +1 is -5. And then we're going to get -5 times by 2t, which is -10t, plus 2t, and that's going to give me -8t. So we're going to end up there with two solutions. We're either going to have the solution t is equal to -1/2, or t is equal to 5 upon 2. And of course, time can't be negative, so that is rejected. Okay, so we write rejected. So t equals 5 upon 2 is the time in which the particle is at rest. Now, we want to find the acceleration at this time. So we're just going to substitute 5 upon 2 into our expression for the acceleration, which was there. So let me kind of go over here, I guess. So when t is equal to 5 upon 2, the acceleration is going to equal to -8 times by 4 times by 5 upon 2 squared. Well, 5 upon 2 is 25 upon 4, if I square it, plus 5, all divided through by 4t squared. So it's going to be 4 times by 5 upon 2 squared, which again is 25 upon 4, minus 5, and then all squared. Well, hopefully what you notice is that those 4s are going to cancel out quite nicely. So gone, 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 gone. And so what we're left with is -8 times by 25 plus 5, which is 30, over 25 minus 5, which is 20, all squared. And so what's that going to give us? Well, -8 times by 30, all divided through by 400. Of course, you can do it on a calculator, but why don't we practice our skills a little bit? We're going to divide top and bottom by 10, like that. And then we can divide top and bottom by 8. So 40 then becomes 5. And so what we get is -3/5, which you could also write as minus 0.6 meters per second squared. Okay, and that should be your answer. I'm just going to check it against the mark scheme, make sure that we're correct. And yeah, all fine. Okay, so here we are in question 7, which is the third question. We are told not to use a calculator. That means that you need to show all of your working very, very thoroughly. Okay? All right, now given that the area of this triangle is 3 plus root 3 upon 4, we want to show that sine 75 is equal to that thing there. Now, how can we get the area of a triangle? We can use the formula, a half AB sine C. Okay? So in this particular case, we want to use sine 75, don't we? So the area of this triangle is going to be a half this length times by that unknown length times by sine 75. And that thing should be equal to 3 plus root 3 upon 4. Now, the point is this. In order to do that, we're going to need to know this length here, BC. So I'm going to label that guy first as X, because we need to find that out before we can do anything else. Now, how are we going to do that? We're going to have to use the sine rule. The sine rule states that this length divided by sine 60 must be equal to that length, root 2, divided by sine 45. So that's what I'm going to do. I'm going to write x divided by sine 60 degrees is equal to root 2 divided by sine 45 degrees. Okay, and if I was to rearrange that, x is going to be equal to root 2 upon sine 45 times by sine 60 degrees. Okay, now we can use the exact values that were given in the question. Sine 45 is the same as root 2 upon 2, or 1 upon root 2. How do they do it in the question? Root 2 upon 2, yeah? And sine 60 is root 3 upon 2. Right, so we've now replaced those things. Well, if we were to multiply out these two fractions, right, we multiply out the numerator. That's going to give us root 6. And if we multiply out the denominator, right, root 2 upon 2 times by 2 is just root 2. So we're left with root 6 divided by root 2, and root 6 divided by root 2 is root 3. Why is that? Well, it's one of the third rules, right? If I've got the square root of a and I divide it by the square root of b, that's equal to the square root of a divided by b. In the same way that the square root of a times by the square root of b is the square root of a times by b, right? So that's that reason. So I can now label this thing as root 3, right? So x is equal to root 3. Well, how can we use the formula for the area of a triangle? We can now say that the area of the triangle is going to be a half root 2 times by root 3 times by sine 75. So I'm going to write that out. The area of our triangle, area, is going to equal to a half times by root 2 times by root 3 times by sine 75 degrees. And we're told that this area is equal to 3 plus root 3 upon 4. So 3 plus root 3 upon 4 is equal to this whole thing here. 4. So how are we going to simplify this? Well, firstly, root 2 times root 3 is equal to root 6 for the reason I've just stated. So I'm going to times both sides by 2 and divide by root 6. So we get sine 75 degrees there is equal to 3 plus root 3 upon 4 times by 2 and then divided by root 6. Okay, well, first thing we can do is we can divide top and bottom by 2. So that becomes 2 on the bottom. And then what we're going to need to do is we're going to need to rationalize this denominator, sorry. And how are we going to rationalize? Well, to get rid of that square root, we've got to multiply top and bottom by root 6. So we're going to multiply this by root 6. And we're going to multiply the top as well by root 6 because it's need to do that for equivalent fractions. So if I multiply the top by root 6, I get 3 root 6. And if I multiply root 3 by root 6, I get root 3 times by 6, which is root 18, all divided through by 2 root 6 times by root 6. Well, root 6 times by root 6 is 6. 6 times by 2 is 12. Okay, so the key thing is that thing times by that thing is 6, and we times by 2, we get 12. All right, well, what's root 18? Remember, you can't use a calculator, so you need to show you're working. Root 18 can be rewritten as the square root of 9 times by the square root of 2, right? Because 9 times by 2 is 18. And the square root of 9 is 3. So what we got here is we've got 3 root 6 plus 3 root 2 all divided through by 12. And hopefully you can see we can divide top and bottom by 3 to get root 6 plus root 2 all upon 4. And hopefully that should, I think, be what you're looking for. Root 6 plus root 2 upon 4? Yep, that is exactly what we want as the answer to this question. All right, then part B, hence we want to find the exact length of AC. In other words, we want to find it as a surd. Well, I think probably the easiest way to do this is to use the sine rule again. So AC divided by sine 75 is going to be equal to root 2 divided by sine 45, or you could say root 3 over sine 60. But I'm going to choose to use root 2 and 45 because it's not something we've calculated. It's something we know. So therefore, if we made a mistake with this somehow, then that mistake is not going to be carried through. Okay, so AC divided through by sine 75 degrees is equal to root 2 divided by, what was it, sine 45? Ooh, sorry. Sine 45. Okay, so therefore AC is going to equal to root 2 upon sine 45 times by sine 75 degrees. And we can now substitute in what we know. So sine 45 is root 2 upon 2. And sine 75 is root 6 plus root 2 upon 4. Root 6 plus root 2 upon 4. Okay, and what's the best way of simplifying this? Well, look, for the first fraction, this guy, what we could do is we can multiply top and bottom by 2. Right, so if I multiply top and bottom by 2, I'm going to get 2 root 2 upon root 2. And 2 root 2 upon root 2. The root 2's cancel off, so we're just left with 2. So that's that. Times by root 6 plus root 2, all divided through by 4. And of course, I can cancel off by 2. So I get root 6 plus root 2, all divided through by 2. And I'm just going to check that that is the right answer. Root 6 plus root 2, all divided by 2. Yep, that is the right answer. Okay, so here we're in question 8a, which is a trigonometric identities style question. We want to show that the left-hand side is the same thing as the right-hand side. And with this kind of question, right, we're not solving to find x, just to clarify. What we're doing is we want to rearrange that so that it looks like that. Now, in order to do this, I think it's just a little bit helpful to say let sine x be s, and cos x be c, and tan x be t, because I just find that otherwise it gets so confusing having to write all these things out. Now then, the left-hand side is therefore sine divided by tan minus 1 minus cosine divided by tan plus 1. So I should write tan x is equal to t, isn't it? Now we're going to use the first identity, which is that tan x is equal to sine x over cos x, right? Sine x over cos x. So that means that I can replace the tan with s upon c. So here I've got s over s upon c minus 1 minus c s upon c plus 1. And I don't like having fractions in fractions, so I want to get rid of those cosine fractions there, this guy here and this guy here. And the way I'm going to do that is I've got to multiply the whole denominator by cos. And of course, if I multiply the whole denominator by cos, I've also got to multiply the whole numerator by cos as well. And the same thing for the other fraction. Right? So often a common mistake is you don't multiply the whole thing. Now then, on the top, what have we got? We're going to have sine times by cos, which I'll write as cos sine. On the bottom, this thing times by cos will just give us sine. And then minus 1 times by cos is cos, or minus cos. Then over here, we've got cos times by cos, which is cos squared, over sine plus cos. Okay, so we simplify things a little bit. Now, what we're going to do is we're going to try to combine these two fractions, and the way we're going to combine them is we're going to give them the same denominator, so we're going to cross multiply. So this will be cos sine times by sine plus cos, minus cos squared times by sine minus cos, and I'm going to put this all over sine minus cos times by sine plus cos. Well, let's expand the numerator. If I expand the numerator, I'm going to get cos sine times by sine, which is cos times by sine squared, plus cos sine times by cos, which is cos squared sine, and then minus cos squared times by sine is minus cos squared sine, and then minus cos squared times by minus cos is positive cos cubed. And then, of course, on the bottom, if we were to expand that, we get sine squared minus cos squared, right? Now, on the top, hopefully what you can see is we got plus cos squared sine and minus cos squared sine, so that disappears. And then on the numerator here, we can factorize out a cos. So if I factorize out a cos, then what I'm going to end up with is cos bracket sine squared plus cos squared, all divided through by sine squared minus cos squared. And sine squared plus cos squared is just 1. It's an identity. So we're left with cos divided by sine squared minus cos squared, and that is the same thing as the right-hand side, and so we have shown the identity. All right, so we're in part B of this question. We want to solve this equation is equal to 1 for x's between 0 and 360? Well, hopefully you should notice that the word hence is important. It means we need to refer back to the previous part of the question, which was the identity. And you should notice that the left-hand side of this equation is the same as the left-hand side of the identity, which means we can replace it with the right-hand side. So that's exactly what I'm going to do. So instead of sine x upon tan x minus 1 minus cos x upon tan x plus 1 is equal to 1, I'm going to write cos x over sine squared x minus cos squared x is equal to 1. And then what I'm going to do is I'm going to try to rearrange this in a way that will be helpful. So I'll multiply both sides by sine squared minus cos squared. So on the right-hand side, I get sine squared minus cos squared. And hopefully what you notice is we've got an equation that is just in terms of cos squared, except for this term here, the sine squared. So it'd be really good if we could get rid of that. Well, how can we do that? We could use an identity. And the identity that I suggest is we use sine squared is equal to 1 minus cos squared. So I'm going to replace sine squared with 1 minus cos squared, like that. And if you're not sure about that, on the front of your exam paper, you've got the identities listed, and you're told that sine squared plus cos squared is equal to 1. So if we just rearrange that, sine squared is equal to 1 minus cos squared. Okay? All right, I'll rearrange this. We're going to get 0 is equal to 1 minus 2 cos squared x minus cos x. And hopefully you should recognize this is essentially a quadratic, right? This is a quadratic. 2 cos squared x plus cos x minus 1, right? So I've just rearranged the terms a little bit, and I've multiplied through by negative 1. Now, to make this quadratic a little bit easier to see, I'll just use a substitution. Let u equal cos x, because if that's the case, we can rewrite this guy as 2u squared plus u minus 1. And I can factorize that. That's going to give me 2u here and a u here. And I'm going to put plus 1 there and negative 1 there. Why is that? Well, plus 1 times by negative 1 is negative 1. 2u times by 1 is plus 2u. And then we're going to get minus u. So 2u minus u is just u. So that's our solution there. And so therefore, we're going to get two outcomes. Either u is equal to a half or u is equal to negative 1. And that means that we need to solve the equation cos x is equal to a half, or cos x is equal to negative 1. Now, there are a couple of different ways to solve this kind of equations. And if you saw my previous video for exam paper 1 variant 3, I used the unit circle method. But we could also use the graph of cosine. So for a bit of variety, I'm going to use that method here instead, just to make sure that it's really clear how I'm getting the answers that I want. So I'm going to draw the graph of cos x, which looks something like this. Okay, so let's try to draw it like that. Like that, like that, like that, like that. Okay, so that's the graph of cos x. It's just one wave, and one wave takes 360 degrees. So that will be 180. That's going to be 90 degrees, and that will be 270. And of course, the cos graph goes between 1 and negative 1. And so if we want to solve where cos x is equal to a half, really what we're asking is, where is the intersection of this graph with the line y is equal to a half? Right, so we want to find those intersection points there. So that guy and that guy. And if we want to solve cos x is equal to negative 1, what we're asking really is, where are the intersection points with the line y is equal to negative 1, which is that point there. Okay, so we want to find those 3 points. Well, if we put that into a calculator, if we do cos inverse of a half, what we should get is 60 degrees. So we get x is equal to 60 degrees there. And hopefully by using the property of symmetry, we should be able to identify that this point will be 360 minus 60. So in other words, it will be 300 degrees. If you're not sure about that, there is essentially what I'm saying is there is a line of symmetry here, right, about the point x is 180. And so these these points here are symmetrical in that line. And what that means is that the distance here to here, which is 60 degrees, must be the same as the distance here to here, which is 60 degrees. So if we want to find that coordinate point there, this guy, we do 360 and we subtract off the 60 degrees. Okay, that's what we do. Okay, then lastly, this point here, if we do cos inverse of -1, what we're going to get is we're going to get 180. So I just put that in there, 180. And so our answers should be 60 degrees, 180 degrees, and 300 degrees. All right, this is question 9. A curve has the equation x e to the 2x. We want to find dy dx. We want to differentiate it. Now, what you want to notice, first of all, is we've got the product of two functions. What I mean by that is we've got one function x multiplied by another function e to the 2x, right? So the word product means we're multiplying two things, like the product of 3 and 5 is 15. What we've got here, if product 3 and 5 is 15 means 3 times 5 is 15. So what we've got here is we've got the product of two functions. So therefore, we need to use the product rule. So we're going to call the first function u, which is x, the second function v, which is e to the 2x. And we're going to need to differentiate these if we want to use the product rule. So if I differentiate u, I'm going to get 1. If I differentiate e to the 2x, now the way I do this is I take the power of the exponential, and I differentiate it. So if I differentiate 2x, I get 2, and I multiply therefore through by 2. Now that's actually a chain rule for those of you who are not sure, right? We've got one function, 2x, inside another function, e to the 2x. So the way we do that is, or another way of thinking about it is, we differentiate the big thing, well, the exponential just gives us the exponential, and then we differentiate the little thing on the inside. So we differentiate 2x, we get 2, and then we multiply through by that. Okay, so a couple of different ways of looking at it. Now, what is the product rule? The product rule is v times by du dx plus u times by dv dx, right? That's the product rule, which I recommend you remember in that order so you don't confuse yourself with the quotient rule, which is v du minus u dv. And then what we've got to do is we've got to substitute in, right? So v is e to the 2x times by du, which is 1, plus u, which is x, times by 2e to the 2x. So we get 2x e to the 2x. And I think it's maybe helpful to factorize this as e to the 2x bracket 1 plus 2x. Okay? All right, then part B, we want to find the equation of the normal to the curve at x is equal to 1. Well, if we want to find the equation of any line, we need two things. The first thing is we need a coordinate point. And the second thing we need is we need a gradient. How are we going to get the gradient? We are going to, how are we going to get the coordinate point? Well, we've got the x coordinates, so what we're going to need to do is to substitute that in to find the y coordinate. So when x is equal to 1, when x is equal to 1, y is equal to 1 times by e to the 2 times by 1, which is just e to the 2. So our coordinate point is the point 1, comma, e to the 2. So we've got that done. All right, the gradient. Now, the gradient of the tangent is given by dy dx. So let's first find that. So we found dy dx is e to the 2x bracket 1 plus 2x. So we can say when x is equal to 1, dy dx is equal to e to the 2 times by 1 bracket 1 plus, was it 2 times by 1? 2 times by 1. So what we're going to end up there with is 3e to the 2. Now, as I said earlier, differentiation tells you the gradient of the tangent. But we don't want the gradient of the tangent. What we want is the gradient of the normal. Now, the normal is perpendicular to the tangent. And hopefully what you will know is that if two gradients are perpendicular, so gradient of tangent and gradient normal, if those are perpendicular, then their product is equal to -1. So if I want to find the gradient of the normal, then actually what I need to do is I need to say the gradient of the normal is equal to -1 divided by 3e to the power of 2. Okay, so now what I got is I got my coordinate point, 1e to the power of 2, and I got the gradient of the normal, -1 upon 3e squared. So now I need to substitute it into the formula for the equation of a line. Y minus y1 is equal to mx minus x1, right? And if I do that, if I substitute in, I'm going to get y minus e to the power of 2 is equal to m minus 1 upon 3e squared bracket x minus 1. Okay, and I maybe want to expand that. So y is equal to negative 1 upon 3e squared x plus 1 upon 3e squared plus e squared. And I'm just going to check the mark scheme, see what answer they give, or rather what form of the answer they give. Let's have a quick look at that. Oh, they were content to leave it in this form, right? So that form would give you all of your marks, but the mark scheme also says OE. OE means or equivalent, right? So if you ever see those words on a mark scheme, OE, it means that if you rearrange it in any way, it would also be acceptable, right? So this thing would be acceptable, and this thing, which I've rearranged, so long as it's right, would also be acceptable. Okay, so here we are in part C of this question. Using our answer to part A, that's the key thing here, find the exact value of this integral. Now, what did we learn in part A? We learned that if we had the function y equals x e to the 2x, and we differentiated it, then we would get this thing here, e to the 2x plus 2x e to the 2x. Now, how can we use this answer to find the integral? Well, if we differentiate this and get that, then the reverse is also true. If we integrate this, then we must get that. Why is that? Well, because differentiation is the reverse of integration, or rather, integration is the reverse of differentiation, vice versa. Okay, so if I take that, differentiate it, and I get that, that means that if I reverse the process, if I integrate this, I'm going to get back to here. So your first step should always be to rewrite your previous answer, your differentiation, as an integration. So I'm going to write the integral of e to the 2x plus 2x e to the 2x dx is equal to x e to the 2x plus c. Okay, now basically you should always do that as your first step with these types of questions, because essentially you're guaranteed, I think, one method mark, right? Because you are showing that you understand the core principle that integration reverses differentiation, right? So this guy here, you put inside the integral, and when you integrate it, it's going to take you back to your original function. Now, having done that, we need to use our brain a little bit and say, what term do we want? Well, we want to find the integral of 2x e to the 2x. So where is that in our integral? It's this term here, right? So that's the term that we want to isolate and get by itself. Now, the way we can do that is to split apart this integral. So I can rewrite this as the integral of e to the 2x dx plus the integral of 2x e to the 2x dx. In other words, I've split that integral up into two separate integrals. Okay? So that thing here is what I want. Now, the other part, the integral of e to the 2x, is something that I'm able to calculate because we know how to integrate that. So if I integrate e to the 2x, I get e to the 2x. Then what I do is I take the coefficient of the power, the 2 in this case, and I divide by 2. Okay? Remember, if I was to differentiate e to the 2x, then I would take that coefficient 2 and I would multiply by 2. Well, because integration is the reverse of differentiation, then what I've got to do is, instead of multiplying, I've got to divide by the 2, okay? If you're a bit confused about that. Okay, so plus here, the integral of 2x e to the 2x dx is equal to x e to the 2x plus c. Well, then all I've got to do is I've got to bring that other term here, got to bring that over to the right-hand side. So that's what I'm going to do. So in the end, we've got the integral of 2x e to the 2x dx is equal to x e to the 2x minus a half e to the 2x plus c. And I think it'll be good practice just to factorize. So what I'm going to do is I'm going to factorize out a half e to the 2x. So if I do that, a half e to the 2x, then what I'm going to get there is 2x minus 1. Okay, like that. Which I'll change those brackets a little bit. because we usually use square brackets for the integral bounds, okay, plus c. Okay, now then, what we wanted to do is we wanted to find the definite integral between the boundaries of 0 and 2. So I'm going to change this now to a definite integral. So if we want to integrate between 0 and 2, 2x e to the 2x dx, then we're going to take this thing, the half e to the 2x bracket 2x minus 1. And we no longer need the c, but we need the square brackets, and we're integrating it between 2 and 0, or 0 and 2 to be more precise. Okay, well, having done that, what we next need to do is we need to take our upper bound 2 and substitute it into our function. So if I do that, I'm going to get a half e to the power of 2 times by 2, which is 4, multiplied by 2 times by 2, which is 4, minus 1, which is 3. And then what I'm going to do is I'm going to substitute in 0. Now, you need to be a bit careful here, right? Because if you substitute in 0, you don't necessarily get 0. And the reason for that is e to the power of 0 here is going to be equal to 1. Okay, so just be careful. Sometimes I see people think if you substitute in 0, this whole thing becomes 0, but it is not true. Times by 2 times by 0, which is 0 minus 1. So now let's try to simplify this guy. I have got here 3 upon 2 e to the power of 4 minus a half. So that's plus a half e to the power of 0, and of course e to the power of 0 is 1. So we can just get rid of that term there, okay? So in exact form, the answer should be 3 upon 2 e to the 4 plus a half. Are we asked to give an exact form? Yes, in exact. So they won't accept the decimal answers, okay? All right. Okay, then, question 10, an arithmetic geometric progression style of question. Firstly, we're told that this is an arithmetic progression. So I think it's helpful to write down the formulas on the front of your exam paper. The nth term of an arithmetic progression is a plus n minus 1 d. Okay, and also you could have Sn, the sum of the first n terms, is equal to n upon 2 2a plus n minus 1d, but you don't need that in this particular question, okay? All right, so let's read it. The fifth term is 11, right? So what's the fifth term going to be? It's going to be a plus n minus 1, so that's going to be 5 minus 1d. So the fifth term is a plus 4d, and we're told that that's equal to 11. So let's write that down. A plus 4d is equal to 11. Okay, well, the seventh term is 3 times the second term. So how could we write the second term? The second term, sorry, not second, the seventh term is going to be a plus 6d. And we're told that that's going to be 3 times by the second term, and the second term will be a plus d, right? Because 2 minus 1 is 1, 1d. Okay, now we want to find the first term and the common difference. Well, essentially, this is going to be using simultaneous equations. So over here, we've got one equation, right? And I think we can just rearrange the second one to make it a little bit easier to handle. So this is 3a plus 3d is equal to a plus 6d. I'm going to subtract 3d from both sides. So I get 3d there is equal to 2a. So I subtract a from both sides. And therefore, a is equal to 3 upon 2 times by d. Well, what I'm going to do is I'm going to take that second equation, I'm going to substitute it into my first, so I'm going to get 3 upon 2d, so 3 upon 2d plus 4d is equal to 11. Let me just check that I got that right. Yeah. And I'll multiply everything through by 2, so 3d plus 8d is equal to 22, so 11d is equal to 22, so d is equal to 2. And if d is equal to 2, then we can substitute that in. A is 3 upon 2 times by d. A is equal to 3 upon 2 times by d, which is 2. Therefore, A is equal to 3. Okay, so those are our answers. A is 3, D is 2. All right, so we're in part B of this arithmetic geometric progression style question. This one is a bit more challenging, but if we're systematic about it, it should be okay. I think the first thing to do is we want to state the formulas for arithmetic and geometric progression. So the nth term of an arithmetic progression is given by a plus n minus 1 d, where d is the common difference. And for a geometric progression, the nth term is given by a times by r to the power of n minus 1, where r is the common ratio. Okay, now there's potential for confusion here, right? If the two progressions had a different starting point, in other words, a different value of a, because we kind of use a in two different ways. But that's not the case here. We're told that the first terms of the AP and the geometric progression are both 3. So we're going to avoid that confusion. And I think, therefore, what I'll do straight away is I'm just going to replace that a with 3. Okay, so in this case, we've got 3 and 3 going there. Okay, so let's try to work through this. The second term of the arithmetic progression is the same as the third term of the geometric. So how can we write the second term of an arithmetic? Well, it's going to be 3 plus 1d. So we've got 3 plus 1d. And that's going to be equal to the third term of the GP. What's the third term of the GP? It's going to be 3 times by r to the power of 2. So we've got 3r to the power of 2 there. Well, the next thing, we've got the sixth term of the arithmetic progression. How can we write that? That's going to be 3 plus 5d. And that's going to be equal to the fifth term of the GP. Well, how can we write that? 3 times by r to the power of 4. Okay. And then we're told the common ratio is greater than 1. So basically what we've now got is we've got a set of simultaneous equations for us to solve. We'll call that equation 1 and that equation 2. Let's do elimination. And I think probably the best way to do it is to take the first equation, multiply it by 5, so we can eliminate the d. So let's do that. 15 plus 5d is equal to 15r squared. And we've got 3 plus 5d is equal to 3r to the power of 4. And then what we're going to do here is we're going to subtract one equation from the other. So we do a subtraction like that. So 15 minus 3 is 12. And 5d minus 5d is 0. And then we've got 15r squared. Sorry about that. 15r squared minus 3r to the power of 4. Okay. Now, I'm just going to rearrange that as 3r to the power of 4 minus 15r squared plus 12 is equal to 0. And we can divide this all by 3, can't we? So we get r to the power of 4 minus 5r squared plus 4 is equal to 0. And this you should hopefully identify is a kind of hidden quadratic. And I'll solve that by saying let u equal to r squared. And if that's the case, the quadratic becomes, or the equation becomes, u squared minus 5u plus 4 is equal to 0. And if we solve that, we will get u minus 4 times by u minus 1, right? Because minus 1 times minus 4 is positive 4, minus 4 minus 1 is minus 5. So we end up with two solutions, u is equal to 1, or u is equal to 4. And therefore, r squared is equal to 1, or r squared is equal to 4. Well, if we square root this, r is either equal to plus or minus 1, or r is equal to plus or minus 2. But the question says right at the beginning that or not right at the beginning, sorry, one of the 4 points, the common ratio is greater than 1. So what does that mean? Well, we can't be negative 1 and we can't be positive 1 because we've got to be greater than 1. So those are rejected. And we can't be negative 2 either. So the common ratio must be r must be equal to 2. Okay, so that's going to be our answer. Well, if r is equal to 2, we can probably find the other guy by substituting in. So let's substitute into equation 1. We're going to get 3 plus d is equal to 3 times by 2 squared, so 3 times by 4. So d is going to be equal to 3 times by 4, which is 12, minus 3, which is 9. So the common difference there is 9, and the common ratio was 2. Well, I think as a good rule of thumb, why don't we just double check our progressions, right? So we've got an arithmetic progression, and the first term is 3, and it's going up by 9. So the next term will be 12, and then it'll be 21. Yep, and then it'll be 30, and then it'll be 39. okay? And then the geometric progression, the first term is 3, and if the common ratio is 2, then we're going to get 6, 12, 24, 48, okay? Now then, let's just check if this kind of makes sense. The first terms are both 3, well, that's true. The second term of the arithmetic progression, which is 12, is the same as the third term of the geometric, which is 12, so that's right. And the sixth term of the arithmetic progression, okay, so we need another term there, don't we? So that would be 48, that's the sixth term of the arithmetic progression. It's the same as the fifth term of the geometric, and that's true. So there we go, and we've got a simple way of checking our working, that it's all correct, and I encourage you to do that. I think here with this question, right, it's going to look very scary, but don't get too scared. Just work nice and patiently through it, and I think it's actually doable. Okay, if you found these videos helpful, guys, please like and subscribe and send them to your friends. And yeah, I wish you well with all your studies.